Log on, tune in, find out. Another good idea from Cambridge.
So, next is David Stephenson from Exeter University. I have a number of interesting anecdotes about David, but none of them are afraid of repeatable. So over to you.
Thank you very much. Not on video, anyway. Right, good afternoon. I thought for my session now, I thought it'd be useful to try and summarise some of the things that came out of our workshop in Exeter in September. But I also thought that I'll throw a few of my slides in that I did in Exeter as well, so people like them there, so you may as well have them as well, right? So apologies for those that were out at the workshop and having to see this again. The people out at the workshop, it's very hard summarising a workshop because lots of interesting things happened. So I've gone through the filter, been data assimilated by me, and I probably got it wrong, right? So some of the people at the workshop, if I misrepresent something or you think something's important, just chip in, please, at that. It would be useful, yeah. We had the workshop in Exeter. The co-organisers were Matt Collins, John T. Rougier and Richard Chandler. And these were the participants, and I think people generally found it quite useful. I certainly found it very interesting. So there were lots of interesting exchanges and ideas, so including quizzing Michael for quite a few hours. It was quite good fun. If you want to find out more stuff, there's actually a Wikipedia pages on the link to the Prom thing, and I sent around the thing to all the participants, so you can actually look at the things that we collected there. So the aim of the workshop was to try and debate the strengths and weaknesses of existing frameworks for probabilistic climate prediction, and to identify and formulate pressing and potentially solvable problems. Right. So I think we have identified a lot of problems. I don't think we really reviewed all the strengths and weaknesses. We weren't so nasty as to do that, but there's a lot of stuff did come out about general ideas and general, more a to-do list for the next 100 years, I think, really is what came out of the thing. This was one of the more inspired moments with John T. asked for a retro device here, the overhead projector. It was quite great watching John T. produce this one slide here, which was a wonderful moment, I thought. And he produced this wonderful framework for us, and he controlled his vocabulary, which was very nice to see him controlling his vocabulary. And it's nice to see somebody trying to formulate climate prediction in a rigorous way rather than the sort of pragmatic way we're used to seeing it in climate science. So I really enjoyed watching this. This developed in front of us as John T. wrote on this. It was like watching Vision On for the old people in the audience. We also tried doing other things, but that didn't work so well on the model bias. It ran down the wall for some reason. Probably explains something about model errors. You know. So the themes, as organisers, we came up with some sort of ideas for themes. One theme was a statistical frameworks for prediction, and that was chaired by John T. We had theme B, which is on the calibration of climate prediction, so bias, correction, looking at model errors. Theme C was on the evaluation of climate predictions. Theme D was on the model process and inadequacies, and theme E we left open for people to decide when they came to the workshop what they wanted to talk about. And after quite an exciting discussion, they came up with, well, we all came up with, what is climate? It sounds stupid, climate scientists saying this, but what is climate? How best to design multi-model ensembles, and how best to communicate uncertainty were the three areas that this theme E came out with. Theme B and D decided that it was better just to join forces together and work together in a sort of model inadequacy team, right? So we pulled ourselves together. So in the end there was a framework breakout group, there was a model bias inadequacy sort of group, an evaluation one, and a theme E which did all the interesting stuff. Yeah. Richard chaired that admirably. Yeah. I'll try and represent bits that came out of all this stuff, right? But one of the first days, the discussion that came out very clearly that the statistical framework underpins most of the other stuff. So without a proper framework, you don't know what you're doing. And I think that's basically what Michael said, but more elegantly. So I agree. So there's going to be a lot in this talk about frameworks, and there's going to be quite a lot about model error. And I'm sorry about evaluation and design of experiments. I'm going to do less on those, but we can try and show some of that. What is climate is a really difficult question. Everybody knows what weather is, I think. You look out the window, you see weather, you know what it's doing. This whole question of what is climate, you know? And what do we mean by climate? And it's not obvious. We had 2 different breakout sessions discussing this because it wasn't that obvious for people to work out what it was. Here's the first set of ideas that came out of the first session. So we don't really observe the true climate. We only observe bits of it, but incorrectly as well with measurement error. and we only observe various components. This is more an idea, so it's useful to think of sort of low-order models, simple models to try and understand what we mean by climate, and I think Tim showed that nicely in his talk. He used a toy model there to sort of really understand some of the ideas. Then there were some ideas about what climate might be. Climate is the invariant measure of a hypothetical thought experiment in which the forcing is held constant indefinitely. So the policymakers like this one, this is it's ideal for communicating to your chief scientist. We try and do that, but humanity has failed to hold the forcing constant. It's what is obtained by taking the joint PDF of the state and the parameters and then integrating it over the parameters. That's probably a Bayesian that came up with that one, I guess, in the breakout group. And the PDF of the current system state given all the historical observations. So those are 3 first shots at what climate is. Another observation of the discussion was that current GCMs don't actually produce probability density functions, they just produce climate runs. And so additional effort is needed, and model assumptions, statistical model assumptions are needed about how to make a PDF out of climate output. And a favourite of Jonty, and not many other people in the workshop, was ergodicity. Richard shied away from it, unfortunately, but ergodicity is one of the issues. So that was the first shot, but to make it more concrete, then there was a second regrouping on this, and the group started to consider what is meant by the climate in a particular place at a particular time. So it said, could we actually consider the climate of Exeter on the 1st of January 2070? Does it make any sense? We know that there'll be some weather on that day, but obviously there'll just be one type of weather on that day. But can we talk about the climate of Exeter on that day? Yeah. We decided that climate, instead of just being a mean or an average, should be more the whole probability distribution of weather in Exeter on that day. So this sounds a bit crazy. You can know that on that particular day there's only one sort of thing of weather. So what do you mean by probability distribution of weather on a day? Yeah? In a place. Well, there's 2 ways we sort of really could do it. One way is to you could think of doing ensemble runs, either with a forecast model or with a data simulation system, and you could try different initial conditions and you'll end up with an ensemble, and from that you could get some sort of distribution under assumptions. The other idea is to make sort of assumptions about homogeneity and trends locally in time and space, and then use nearby observations to actually then try and get a distribution for you at Exeter. So this is traditionally what people do in climate when they say climate is a 30-year average or whatever. They basically assume stationarity over the 30-year period and then sort of looked at the successive time values to get an estimate of climate centered on that 30-year period. So this idea of 2 different approaches really to sort of how you could define climate, and you could actually mix those 2 as well if you really wanted. So we could talk about this more if you want. I mean, maybe you've all understood what is. Do you all understand what is climate? Oh, sorry. Yeah. Uh-oh. Subjective Bayesian in the audience. You're going to like this, actually. Yes, a good point you make there. The point you should realise, which you've actually beat me to it, is that both these approaches actually depend on sort of probability model assumptions, right? So if I use a different way, different sort of modelling assumptions in here, I'll get a different definition of climate, right? And so there is not a single probability for this. There's more than one probability, as Michael points out, and it'll depend on how you set up your models. Yeah, you happy with that? Yeah. Okay. So there's a very famous Bayesian statistician, which some of you will recognise. Recognise him? Anybody? You should recognise him. This is Bruno de Finetti. Yeah. Yeah. Unless I got the wrong thing off Google, but could be Bruno's brother or something. But Bruno de Finetti is very famous for his works on Bayesian statistics, fundamental works and foundational studies. And at the beginning of one of his books, he says, probability does not exist, right? And the reason he's sort of saying that is that if you go outside and look around under the trees out there, you're not going to find a thing called probability. Probability is a model construct. It will depend on how you make the thing. It's a man-made concept. And that's a very important thing to remember with probability, that it's not an ensemble of simulations is not a probability, right? A probability needs a probability model. So I think because climate is a probability distribution of weather and probability doesn't exist, I've got a new saying. I don't think climate exists, right? And you with me? Anybody disagree? And then what we're trying to do in probabilistic climate prediction is using non-existent probabilities to forecast non-existent climates, right? So that's why the problem is so difficult, you know. I'm happy with this. Well, I agree. By non-existent, I mean that it's actually a model concept, not a real thing. So if you said weather, that would be wrong. Weather does sort of exist, right? So, yeah.
So your first definition talks about an invariant measure of some dynamical system. I mean, that's a well-defined concept, isn't it?
Now that's a good question. That depends on your dynamical system, which is a model, right? So that's a model concept. We decided actually that climate probably exists in certain dynamical systems, but the real world is not a dynamical system. The real world is the real world, right? You might like to think if the dynamical system is an approximation to the real world. It is, but this is subtle, you know. Yeah. Basically, every way you think about trying to define climate is model dependent in a way. Yeah. So we can argue about this for the next hour later on if you want. I'm happy for this to be on the web. As a climate scientist, I hate the fact it doesn't exist. It makes my job a lot easier. Okay, so obviously, if we agree with this stuff, then how we actually do climate and probabilistic climate prediction obviously needs a statistical framework, a statistical model. It's fundamental. It's not just a bunch of weights. There's actually something really important here that has to be developed. So some people like to do just a weighted sum of different multi-model runs. So you take xi's, the different runs from different bunch of multi-model experiments, weight them and then get some multi-model means. So people are very fond of this weighting thing. Well, there's no distributional assumptions in there. People incorrectly interpret the weights as probabilities for individual models, and they're not. They're just weights. To be able to actually work out the variance of this thing, you need to know how the models are dependent on each other, the dependency structures. You have to make assumptions about the covariance structure or the second-order exchangeable structure in the multi-model. You're not really interested in x dash, you're interested in the real world, y, real climate, and you somehow have to work out how x dash is related to y. And you know, the real world is not equal to x dash. Multi-model mean is not the same as reality, right? So you need a statistical model to link the two. So people say multi-model weights and weights are the way to go. They've only got half the story. I mean, there's a lot more to it here. You need statistical assumptions, statistical framework to do this. Jonty came up with his view of how to do this and came up with a very nice framework, and I'd encourage you to have a look at Jonty's talk, which I thought was really good. I'll talk to Jonty even better. So we'll go through some of this. To make this a bit easier, I'll probably show you a different way. We saw one of these the other day. So this is really what goes into climate assessments. A few of us are involved in the next IPCC, and this is the sort of thing that is produced from things like, this is CMIP3 SRES scenarios, a bunch of different model runs. You notice in here, it's not anomalies, this is in degrees Kelvin, right? And you notice, as Tim pointed out the other day, that there's a hell of a spread in there, you know? Nasty mess, right? From that, so we get that multi-model ensemble, and then from that, and you can also see sort of structure there. Certain models are similar to one, some are very different. There's all sorts of things going on in there. And from that, we suddenly produce that, you know. That's what appears in the policy summary for policymakers IPCC. Now, how many people in the audience know how this thing was made? 2. Now, this worries me. This worries me more than supercomputers, that we use supercomputers to run all our climate models, but how these intervals were produced on this thing is very ad hoc, and the judgment statements are very dubious and very this is something that is very, very doubtful about how this was done, and it wasn't done with a nice statistical framework. It was expert elicitation would be a polite way of putting it. So I think we've got a problem here. We've got a bottleneck. We've produced all the runs and we produced that, and then we produce this thing, which is based on sort of a bit of bodging, really, you know. So put it another way, Tim made a point that data assimilation is kind of important. So you go from observations in the real world and try and get them into your model. Then you run your ensemble with your model. Well, you've got the same problem here. You've got your things living in model world here. You've got to get them back into the real world again. So there's a need, a dual of data assimilation to get your forecasts out of model world back into real world. And there's a nice analogy between the two things. And I agree with Tim that maybe data assimilation has something, the map in here will have something to say about the map in there. So it should be, this should help inform that mapping a little bit. You know? So that's the Palmer hypothesis, I think, you know, that data assimilation has got something useful to say. And this is the issue here of how do we get from this thing down to here. But it's worse than that. This is the single model I'm showing. we've actually got multi-models here. So we've got a multi-model space, and we've got to get from that back down to into the real world. And that's if you've only done the model simulations, you've only done part of the problem. You've not actually solved the real world problem. So, rather than talk about multi-models, I got a bit inspired when I was doing the workshop. I thought about Isaac Newton and these large fruits you see all the time. You see apples everywhere, you know. And I'm going to try and explain some of the ideas using my fruit bowl. So, this is a multi-model ensemble. This is my fruit bowl at home, or was in the summer. This is a bit like a multi-model ensemble. There are certain models in here. There's a few of the same ones there, a few replications of that model. There's quite a few of that model, a few different model there. Some model with a bit of documentation on it. Yeah. Rare. So this is what politely is referred to as an ensemble of opportunity, or fruit bowl of opportunity, as I call it at home. Sometimes statisticians call it a fruit bowl of convenience, right? A sample of convenience. So basically, there's nothing random about this. Yeah, I went to the supermarket and bought a few apples and oranges and things and threw them in my fruit bowl, right? I didn't put certain fruits in there because I don't like them. Yeah? So this is not a random sample from all possible fruit. This is me going down to the supermarket and sucking it. And that's exactly the same with the multi-model. It's not a random sample. It also doesn't include all possible fruit. You know, it's only a subset of possible fruit. So that's what we basically got with the multi-model ensemble. And then we got the question of what does reality look like, you know? So does reality look like? Well, I think reality actually looks something more like that, you know, which is this is actually called a durian. It's an inconvenient truth in Singapore because you're not supposed to have it smell so bad, you know. But reality is complicated. It's spiky. It's got really complex things on it. It's difficult. And what we produced is a fruit bowl, a multi-model with our fruits in there. They say something about this. You know, my fruits don't look like elephants, you know, and they look similar to this in some respects. Not very similar, but sort of similar. So this is your true climate, and that's actually, we don't even get the true climate. We actually have to infer that from observations which have got measurement error on there as well. So it's you can't even get y really. You measure z and you try and infer y. You try and infer this thing. So the question is, how can we say something about this reality based on my fruit bowl? That's the question. Yeah. So one way that people do it is they say that a smoothie is a weighted average of fruits. As you people get papers for writing this stuff. You know, there are actually papers published saying this. But an important point is that a smoothie is not an item of real fruit. You know, it is not the same thing as reality there. You can see there's a slight difference. There's also, there's not a unique choice of weights. I can make smoothies in all sorts of different ways. So there's quite a few of the climate science community going out there making smoothies at the moment. There's quite a smoothie industry developing. Yeah? And actually they're producing something that's not really what we want. And I think Richard's probably going to say more about this in his talk. What you really want is realizations of possible reality in the future. And so you want to be able to sample from the distribution of y given your multi-models. You don't want an average of multi-models. That's not really what you want. You'd like to be able to have realizations of possible future reality, future climate. Yeah? So we really want to be able to produce samples from the posterior distribution with all the nice space-time structure you need for impact models and things. We don't want to just have a nice mean, which is an average. I mean, Matt showed a few averages, and the problem is no single thing will look like that. You know, it's washed out quite a few things. There's a funny buzzing noise. So the other question is, should you use all the fruit in the fruit bowl? And this is another debate that's quite hot at the moment out there. Some people are saying, well, we should select models out. We don't want to just weight models. Some models are just downright wrong. You know, some are plain wrong. And you can see here, this fruit looks a bit dodgy. Maybe you just throw it out the fruit bowl, yeah? Yeah? And that debate's going on in climate science at the moment. And actually we do that because we do that every time we do a CMIP assessment thing. We take the fruit bowl and throw all the old ones out and get a new bowl of CMIP fruit, yeah? So we actually do model selection every time we do a CMIP exercise. I haven't seen many people who've combined all the CMIP outputs and used them all together in a massive multi-model ensemble. So. Oh, okay.
Your phone's on. Yeah. Turn it off.
My phone, yeah. Oh, shit.
Turn it on the air.
Sorry about that. It's purposeful jamming device, you know, that was so the question is, if you've got a multimodal ensemble, should you throw some of them out? And I think we're going to see more of this debate on this. Famous quote by Granny Smith, all fruit are wrong, but some are rather tasty, you know, so this one is. So here's an example of, this is the Goldstein-Rougier, or the Rougier-Goldstein way of doing fruit. So this is a homogeneous subsample. So I've basically thrown out all the fruit that don't look similar, right? So some people make assumptions, statistical assumptions in their framework, that they're identically distributed or second order exchangeable. You want the fruit to look a bit similar to each other, right? So I've thrown out all the other stuff, and I've ended up with a nice bunch of homogeneous looking fruit. And there's different ways. There's this independent thing, which is very hard to do. There's also the second order exchangeable, which is more pragmatic and more workable and probably more sensible. Then the question, though, how do you then relate this nice homogeneous set to this? I mean, the argument is because they're all more similar, then it should be easy to probably relate to that. But there's an issue here that by throwing things out, you might have lost something as well. You might have thrown, there might have been a durian in my fruit bowl, I might have thrown that out and kept the apples, you know, so. So you've got to be, model selection could lead to problems if you're not careful. So there's a Granny Orwell came out with a phrase, all fruit are equal, but some are more equal than others, right? So you're probably not eating an apple from Granny Orwell's apples here. So, but there is a question about, there's also a problem with this politically with modelling groups. Modelling groups will not want to see most of the CMIT5 thing being thrown out and just a bunch of models being retained. Climate scientists will probably object to that a little bit. Some of the other discussions came out. One of the interesting things that was noted in the workshop discussions that all these frameworks, statistical frameworks, are really just simplifying assumptions. All models are really simplifying assumptions about the world. We've got a very complex multi-model ensemble, and to be able to make any progress with it and relate it to reality, we have to make some simplifying assumptions. So think of it as a restriction, if you like. The frameworks are a simplified view of the multi-model ensemble to allow you to then do some of the inference. Yeah. That's a useful idea. The models actually can be based on either Bayesian judgments about what's in the fruit bowl and their relationships, or some people in recent years have been using sort of frequentist ideas about this is a sample, a random sample from a population. Right? There was a big heated discussion about sampling and frequentist interpretations, and it came up with the thing that if I got it right, it said that if you are going to have a frequentist interpretation, sometimes that's useful to communicate with people. It's not necessary if you're doing Bayesian judgments, but it can be useful. You should try and think of a way that the population of all possible fruit could have been produced. So you should think of a way that whole population that you're supposed to be sampling from has occurred, and you should think of a way of how you got your sample from it. You know? So the onus is on you, if you like frequentist interpretations, to come up with that. And 3 different ideas came out as to how you might do that. One was, you can imagine thinking of a bunch of different model components and then randomly sort of flicking a coin and deciding whether to couple that component into the model or the next one. So you say, keep this ocean model, flick a coin, no, we'll use the other ocean model. So you could use a randomization, a device, if you like, a coin, some random device to try, and then you could have a random model that way, you know, by randomly coupling different bits of your model. People pointed out that's not how climate modelers actually do it. They do it by being in a room with other climate scientists and make decisions about which parameterization should be in the model. So there's more like expert elicitation or judgments by scientists about which scheme should go into the model. So that instead of the coin, you've got more like an expert judgment on the different components. There was another idea which even I thought was really nice, was that it came out about the evolution of models, so that models are a bit like animals, they're sort of evolved, you know, there's species of them, so it's not supposed to have a fruit bowl, my fruits have evolved from something, right? Some of the fruits are pretty damned horrible and have died out, right? And then you end up with a bunch of what Richard referred to as viable species. Yeah, you put that on the wiki. So the idea is that, you know, climate science is constantly evolving models. Certain ones by survival of the fittest or whatever carry on, and then the other ones sort of wither out and new models appear. So there's a bit like an evolutionary tree. And the idea, to understand the structure between the models in a multi-model ensemble, one idea would be to try and create a sort of family tree of these models, an evolutionary pathway to work out which models are related to each other. You know, we're starting to get quite a few generations of models now, so you could try and understand the dependency by its family connections. The thing that came out as well quite a lot was that a lot of these modelling frameworks and their assumptions should be clearly stated, and they should be rigorously assessed. So these statistical frameworks are being used at the moment in climate science, but have not really undergone this sort of treatment, you know. And that's very dangerous, because people are then using things that the assumptions are plainly not justifiable, and you then make false inference, right? So not good. Okay, moving on to model inadequacy, biases, errors, all that. There's this equation, seen it in various forms today, but this basic reality at y, f of theta is the output from your climate model, theta is your climate model parameters. Obviously your climate model output doesn't quite look like reality, so there's sometimes a bias on here, a discrepancy term, d. And there's also, in climate science, people are doing multiplicative scaling. The ASK method that you saw the other day does multiplicative scaling, so there's a multiplicative bias as well as an additive bias. And I should say these B's and D's here, think of them as distributions over the different models, right? So you've got an equation here of trying to relate reality back to your model, and it can get quite nasty, this. It can actually get worse than that, because how do you then know how your bias might change in time? You know, will your model bias stay constant in time, or will it change in time in complicated ways? Your model bias could actually depend in a very non-linear way on other variables. Dave Sexton's got a great example of that, of snow in Scotland, nearly spoilt the whole UK SIP thing, because basically the D became very dependent on something else. It was very non-linear and very unpleasant, really, what was happening with the bias there. And so this is really complicated, getting this sort of discrepancy terms sorted out in models. It's not easy. And the group that discussed this came up with, could you actually, I'm going to show you some examples, but different ways of bias correcting, you get different answers coming out from climate models. And one idea is, could you unify that by using the statistical framework and get it all in there nicely? Could you then get a nice comprehensive framework for doing that? The answer is probably yes to this, but it remains to be done properly. I think that was the main point of that one. I've said the thing about the time dependency and the non-linearities in these things are complicated, and it's not easy for climate scientists to say what they think the discrepancy term should look like. You know, they made a climate model, they didn't expect it to have a discrepancy, so it's very hard for a climate scientist to say, well, I thought the error would look like this, you know. It's quite hard to elicit that from a climate scientist. The other one was, one way to try and get at the model errors was, rather than the statistical frameworks, this came out a bit earlier today, the statistical frameworks have talked a lot about model parameters, but instead of just having model parameters in there could be a process level in the statistical framework that talks about the physical processes. And if that was in the statistical framework, you could then use that somehow to try and diagnose some of these things. You might be able to get a bit further by using the physical processes rather than the model parameters. There were some questions about how would you test if this was right, if you'd actually picked the right sort of bias things and worked out how to do it properly. How would you know if you'd done it right? And there's some problems of whether you can do it right. And then how would you do it for more complicated things? At the moment with the frameworks are doing things like 30-year means, but suppose you were doing extreme events or something, people want to know about extreme events, regional extreme events, what would you then do here? Because that's getting a bit more complicated, and a statistical framework for doing extremes would be really hard to do. But it's what society is asking for from climate change. And there was a wonderful quote, which I haven't given for his own sake I've not mentioned his name, but it made me laugh a lot. He said, modelling centres have very few B'ers and D'ers, but too many F'ers. Right, unfortunately he's not here, but it's true that we've put an awful lot of effort into developing the climate model, hoping that F becomes equal to Y. Reality is that there's still discrepancies in models. Blocking is still a problem. There's still things that haven't been sorted out in models. So there is going to be a need to sort out the B's and D's, right? There is a need to sort out the B's and D's. I'll give you an example. This probably makes it a bit clear. There's some work we've been doing in Exeter. Calibration strategy is one way you could say, well, I think the model is the same as reality, and ignore it. Not so good. The other one is bias correction, change factor, and then there's other methods. But let's do bias correction, change factor. Imagine you've got present day observations and you're trying to predict some future observations. And you've got some present day climate simulated data and you've got some future climate simulated data, right? This is just time slice stuff to start with. So bias correction, what people are doing normally in the way they calculate the anomalies is they say there's a relationship between y and x, which is a sort of constant. It's a constant function, let's call it b. And that function stays the same from here over into the future. So you work out the relationship between present-day climate and present-day climate simulation, and then you apply that same relationship to the future climate simulation to get your future observations, right? And that's what most climate modelers are doing when they do anomalies and bias correction. They're doing that. Basically, the standard anomaly procedure is not even not just a linear function, it's usually quite often just an additive thing. So there's a difference between y and x, and then you add that difference to this x dash to get this y dash. Yeah? So that's bias correction. There's another way of doing it though on this diagram is change factor, where you say, well, you can look at how your climate model changed from here to here, the transformation there, and apply the same transformation to your y variable here to get to the future y variables. So you said, I'm not going to do bias correction, I'll just, so if say your climate model warmed up by 2 degrees here, you'd take your present day observations, add 2 degrees to them there, and you'd get something that you'd hope looks like future observations. So there are 2 different pathways on this, yeah? And they're being used in the climate side. And what's interesting, I've got some examples here. There's some daily temperature in London. This is from a regional climate model up here, 1970 to 1999, and this is 2070 to end of the century. And these are the observed ones. So the question is, how do we use these 3 sets of data here to get some idea of what will happen in the future? Now, you can look at the PDFs, it'll probably get a bit confusing here, but there's one for present day observations, that's present day observations and the present day climate run, and then this other curve on here is the future climate run. So you've got 3 PDFs here, but none of them are what you want. What you really want to know is what the PDF of the future world is going to be. Yeah? Just to keep it simple, in this case, you could actually forget about any changes in the shape of the distribution and work out the bias correction. If there's no change of the shape, it's just a linear transformation. It's this basically future observations, that your best way of doing them would be this little transformation of future greenhouse gases, future climate runs, sorry. Change factor, your future observations are just a linear transformation of present day observations. So you can go through this and you get these little expressions. You can work out the means of these and you find out they're different. Yeah? For this case for London, in this regional climate model, you actually get a warming of 3.6 degrees there, but you get 4.1 degrees there. Yeah? Now you could argue that both approaches of bias correction seem eminently sensible, you know, or you could think of doing, people have used both both those ways in bias correcting climate models, and you get different answers. Yeah? So there's a bit of an issue here about how we do bias correction in models, and that's why we do need a statistical framework where we can put this in properly and get a unified answer out of the thing that makes some sort of coherent sense, you know, because we don't want contradictory answers coming out of this. Yeah? It's embarrassing this when you talk to decision makers. Yeah? Even worse for this, we did this for extreme values actually, looking at the tail of the distribution. It's got a bit more complicated with the change of shape, but this was actually the 10 summer return levels over Europe in temperature, so we're looking at heat waves. This is with no calibration. This is the change you got just straight from raw model output in the future minus present day observations. This was with bias correction. This is with the change factor method. And you get radically different you even get qualitatively different pictures here. It's warming, a lot more warming up here in the Ukraine and that Scandinavian area. Down here you actually get more warming, it's actually warming here and less warming up there sort of thing. So you know, these 2 pictures aren't even qualitatively similar, you know, so it's slightly upsetting that, you know, you kind of hope that your projections won't depend on how you well, they do depend on how you bias correct, right? That's what this is telling you. So there is an issue there about which is the right way to bias correct, yeah? And one of the dangers with anomalies is that people say, I just did an anomaly. Both of these methods are, in a way, using anomalies, but they're defining anomalies in different ways, right? And you're getting different answers. So anomalies are bias correction, but they're you've hidden it under the carpet a bit. So what we're trying to do here is bring it out into the open a bit, and we have a proper discussion of how to bias correct. Theme C was about how to evaluate predictions. That all this group did, as far as I can work out, came up with questions, but they didn't come up with any answers, or didn't put them on the wiki. So unfortunately, Chris Ferro's not here, but unless he's got the answers and he's writing the paper at the moment, but he hasn't told me about it. So they came up with some really good questions, actually. One is, what is a good climate prediction and how can we measure the goodness? So this question has been asked about weather forecasts in the past by Alan Murphy, what makes a good forecast. And Chris basically is repeating Alan Murphy here with this question, saying what would we consider to be a good climate prediction? Yeah? And then how would you measure the goodness of that? What can we use to actually get at this question of the quality of the forecast? One is you could try and validate your climate models. That can give you some information. If you see the model hasn't got a monsoon or something and you're using it to do a monsoon prediction, that might worry you. You can use short lead predictions to inform you. That's what Tim was making the point about seamless. Information from shorter timescales can help give you confidence in the different models. You can do perfect model experiments where you pretend that reality is one of your climate models, and then you can play games with that and see how good the model is at predicting another realization of that model. You can look at past performance if you're doing seasonal and decadal type stuff. You can look at the hindcast and see if you can get some skill out of that, but still there's a lot of work to be done on this area. And the most important probably is your expert judgments about the actual ability of the climate models to do these processes. So it's about the experts being honest and transparent, and what Michael was saying. So it's not really easy to build up confidence in your climate predictions. So it's really a question of all of these things together help give you some confidence. Yeah. One of the issues they discussed in this group was there's double counting going on, or there could be, because your climate models, when they run them, people have a run and see if it looks like historical climate data. Most of that's in the last century. And so somehow the model, they haven't maliciously tuned the model to look like reality. Climate scientists don't do that. They wish they could, but they can't. So they run the model and then see if it resembles a bit reality. If it looks completely different, they might go off and change the parameters and do something different. Yeah. So there's a danger that you've actually used the same historical observations to sort of tune up your model, and then you use them again to evaluate your model. So you've actually got double counting in here, and that's a danger that you give yourself overconfidence in your model. Then, so you can be careful with that one. Ideally, you'd use independent data. You tune your model on one set, and you evaluate it on another set. Would be the nice way to do it. So there's ways of trying to discount that statistically, thinking of ways of how you could take account of that double counting. Now, you're interested in this. There's only two things. Oh, you're there. You're actually. Oh, great. Well, you started this. You wrote this. Didn't you? Oh, somebody did. I suppose the design of experiments, the 2 points. One point is that there's a feeling that, design of experiments, computer runs on climate models take a lot of effort to do. So just running them without thinking about how to design them is kind of stupid. So there's a niche area that needs to be developed of a bit more design of climate model experiments. And you're starting to see bits of that happening out there. There's some stuff going on, NARCAP and things. There are people thinking about how to design experiments a bit more than they used to do. There's also an idea in here that you can do perturb parameters in one model, but you also want to do design of experiments for multi-models. One of the ideas was sequential design, that basically you use ideas from your previous, CMIP 5 carries on from CMIP 3 or whatever, so you've got ideas from the previous ones, and ideally the previous stuff informs you to help you design your next set of experiments. So there's a sort of transfer of knowledge. You're doing a sequence of experiments really, so it's sequential design is potentially very handy. I don't know if there's, what else? Do you want to add anything on this? There's things about how you do it for extremes, which is obviously interesting.
I've only read the 3 writers so far, so I don't know if I have anything to add.
Anybody else here would like to add anything about design of experiments? Because I wasn't in this session, and I agree with the idea that we should design them. There was an issue about design is a bit tricky because experiments get used for many different things. They're multi-purpose, so that makes it a bit hard to design. Ideally, if you had design experiments and you were just using them for one thing, then you could design them optimally, but it's hard when the climate experiments get used for lots of different impact studies or whatever. It's not obvious how to design it for multi-purpose use. But I don't know if there's anything else to add to that. We'll leave that probably. I had 10 questions when we did the workshop. We got sort of a list of 10 questions which are on the wiki, but I've sort of tried to boil them down to less than 10. And these are what I think are probably some grand challenges, and we could debate them. And if we missed any, we can have a discuss about that in the discussion bit later on this afternoon. I think there is a need to reconcile operational and conceptual definitions of climate and climate trend. this thing about climate scientists not really knowing what they're talking about with climate is getting a bit embarrassing. We had that already in here. Statisticians have noticed that and said some of the confusion we were having in our debate was because people had different ideas of what they meant by climate. Richard Smith recently at a WMO meeting in Paris said there's a problem here that people don't know what they mean by climate trend, and he's right, that the way we define climate trend is rather varies quite a lot in climate science. Yeah. So there's a bit of a need to try and sort of tidy this up, and there's a lot of discussion about baseline periods and changes. There's some issues about that came out of IPCC. So in a non-stationary world, the life's getting a bit hard trying to define what we mean by climate, and we need to clarify that a little bit. The second one is actually to develop statistical frameworks for multimodal ensembles that can actually be used to make reliable predictions of societally relevant sort of variables. I don't think we have those yet. I think there's some early stages in this science, promising science, but I don't think we actually have one of these things. A bit controversial on this. An ideal one would have something that would actually incorporate process information from the models, physical processes. It would somehow be in there. There'd be some way that would come into the statistical framework. Probably by, as Matt pointed out, physical metrics are here to stay, but somehow the information about physical process from the metrics somehow go into the statistical framework and inform it somehow. The framework would have to be able to deal with very complex biases. The models have very complex error structures, and so these nonlinear time-dependent errors and things like that, they do exist in our models, and we need to have a way of sorting that out. And hopefully a nice framework would actually help inform us about the design of experiments of future MMEs. So there could be a nice spin-off from the actual statistical framework telling you how you should optimally design the actual experiments. So if we got one of those things, that would be quite nice. That would be quite useful for climate science. Very useful. Also, if you did have these sort of things, you'd also want to have a rigorous evaluation procedure for assessing these sort of frameworks and trying to build confidence in this important part of the climate system. This is part of climate prediction, is this final bit, right? And so if we don't evaluate these things, they haven't been really evaluated or compared very much in the literature. So we're using things that haven't really been tested or criticised properly, and there's a bit of an issue there. So I think we do need to be a bit more. These are statistical frameworks, are sort of models in their own rights, and need to be discussed and criticised properly. The final one is find better ways of communicating the various sources of uncertainty or certainty in probabilistic climate predictions. There's some ideas about dynamic graphics being quite good. There's some areas. David Spiegelhalter has got some nice stuff, but there's some very nice ways of trying to communicate uncertainty honestly to people. And it's about trying to communicate best judgments as well. I agree with Michael about that. So it doesn't matter if it's not objective. It just matters that we have to be transparent. Those are my Santa's wish list. So I think I'll probably stop at that point if that's okay. I've probably done a bit quick, but thank you.
Do we have some comments or questions?
Well, just to be specific then, I mean, you mentioned just now about models having trouble with blocking, for example.
Yeah.
So let's assume that's true of all your models in your multi-model ensemble. So how do you develop a statistical framework for making reliable predictions in an ensemble, none of whom can do the current weather?
Yeah, we had that debate, and we had a debate on the bias thing about if the biases were so large, should you bias correct or should you just say they can't do it, basically. And I suppose that's a question of model selection. The question of the question about how you weight your models and the statistical framework. There's also a question about model selection and which models are adequate. If the model hasn't got a blocking events in it, then you're probably not going to get very good predictions from that model. It probably shouldn't be in the fruit bowl, right? So, but we need a way of throwing things out of the fruit bowl, really.
The fruit bowl will be empty on the current account. So how do you deal with that? You just put here be dragons or something in over Europe?
Well, no, some models do have things that resemble blocking, right? It's not as... Are you talking about blocking or are you talking about everything?
Well, just read AR4. I mean, most models have trouble with EMSO, they have trouble with MJOs, they have trouble with MJOs, they have trouble with Hilliker.
Yeah.
A lot of stuff.
We could imagine a scenario where there was a tenfold increase, or a whole winter was blocked, and that would be the most extreme scenario. Could you somehow build that in through some sort of...
Yeah, I think there's probably things, you're right, there's probably things where you say the model's got the thing but it's a bit weak, but we can bias correct it. And then there's other times in the model when you say, well, it hasn't got the thing at all, and therefore we can't use that model. You know, to me, there is a. I sound like Lenny Smith when I say this, but there's a point, a stopping point, where you say that model can't be used. You know?
Can I just pick up now? I mean, let's be clear. We took a model that doesn't have blocking. What you're saying is that the standard model and its standard parameterization doesn't show the right blocking statistics. What we don't know at this stage is if we explore the parameter space, whether we would find other model variants that had better characteristics. Because at the moment, no one can afford to, or has the inclination to, explore the parameter space.
Yeah.
So to say a model doesn't block, what you're saying is that one particular choice of the parameters is not right. So the first thing I would say is you have to increase your scope to think about model variants that have not been ruled out by measurements. And that means you have to explore the parameter space. Perhaps you'll find better model variants in that parameter space. But if not, exactly as Matt suggests, you don't carry on with a model that doesn't block. You say the model doesn't block. Order of magnitude, what's that? 2 degrees maybe, plus or minus 2 degrees in mean winter temperature. You carry on with order of magnitude. You don't just say nothing. Right? You have to get out there and make a statement about your judgments.
So our expectation would be, I would think, that no matter how much you fiddle with parameters, you know, it's probably something like resolution. You know, which is
Yes,
important.
I mean that's true for blocking, but let's think about all the other things you might. Yeah.
It's not easy. I mean, ideally we'd have models that look like reality, but they don't sometimes.
At the back.
Well, blocking is probably a soft example. Another example would be the Gulf Stream in the ocean.
Yeah.
So none of the climate models.
That's actually on our wiki page, and I'd advise you to read. Jonty mentions that as an example. I think you wrote that bit or something. Did you? Somebody wrote that. Basically, it said if say Gulf Stream was missing from your model, could you retrofit the model somehow to get around it, right? Now, I don't know what they meant by retrofit. Actually, did the person write retrofit on the wiki actually come forward and explain what they meant by that? Flux corrector, something like that, yeah. Basically mimic the thing, you know. Parameterization scheme, probably.
Yes, actually, the question I was going to do is kind of like this. In your f of y, if your f of y has a null space and you don't know what it is, for example, Pavel gave one instance of a null space of a set of ocean models in the Gulf Stream, and Tim gave a null space and the ability to get blocking. But this presumes you know what the null space is. I mean, is there any statistical method, I mean, maybe the Dempster-Schaefer theory we just heard about earlier this semester or something like that, to put in the possibility of a null space that you haven't actually defined yet?
Maybe. Do you want to field this one? Sounds like a very statistical.
Bayesian inference.
Does your f of theta basically goes to 0 or something? Or is that what you're saying?
Yeah, I mean, you have an inversion in there. So, I mean, you know, if you can't invert it, or if you can only invert on a subspace of it.
Or you can find the rank of your function and see what the rank condition is, and that tell you what kind of a space you would have.
Richard?
In practice,
The range.
with GCMs?
If I understand the question correctly, what you're saying is you have identified that of all of the climate simulators available to you, none give you any information about a particular aspect of the system that you're interested in. And in that case, the statistical framework is perfectly clear. Your posterior is equal to your prior. And you know, you've learned that your climate simulators are uninformative about that.
Yeah.
You know, that's all that you can say, I think.
Yeah. Yeah. Right.
Sorry, I guess it rather depends on the question you're trying to answer though, because if you want to know about the temperature over Europe and you need to know how much the blocking affects temperature over Europe, the fact the model doesn't do blocking very well, but making a prediction based on all the other things that you know as well.
Right.
So somehow you have to build in there the information you've got about how much the thing you're not predicting very well influences the thing you're trying to predict. If that makes any sense.
Yeah. Yeah, and I think that's an interesting question. You ask yourself, where does the multiplicative bias term come from? You know, you said that the additive bit, you say, well, the model's not got the mean state right, but the multiplicative bias term's a bit more, you know, why should you have to scale your model you know, why is the model missing variance or something? You know, you basically said that your model hasn't got enough variance or it's got too much variance, and you're having to scale it somehow, you know. So that doesn't sound very physical to me. So people doing scaling in climate science, there's an issue behind that, you know, why do you then, bias adjustment is bad enough, you know, with the means, but the fact you have to multiply your models by something to correct the variances, that's probably the missing process thing. But, yeah, they don't really justify it very well why there is, why you have to multiply by a number that's not 1. You know?
But it's not to correct the variance, it's done to correct the
Trend.
the trend or something like that. So.
Well, that's a sort of source of variance, isn't it? I suppose. Variance on long time scales, right? But yeah,
it's correcting almost for a structural error in some. It could be like just a missing forcing or misspecified forcing.
My feeling is there are things the climate models aren't. Tim's gone, so I can say it. But I think the models do capture some things, right? So, and some of those things they don't get them perfectly. So there's obviously a need to address the discrepancy and the bias issue. You know? And then there's probably other things that models will never do or never can do. And you know, I don't know. There's.
You raised the very interesting question halfway through the talk about the issue of double counting, or where data is being used to calibrate and to test.
Yeah.
And that seems to me a real danger in the absence of any particularly consistent Bayesian or frequentist framework. But you also made a very interesting comment about that there were ways of discounting had double counting taken place. So I wondered if you could just say a few sentences about that.
I wasn't in that discussion. That was Chris Ferro who was leading it. But Chris would probably say that. But they were talking about. You can, for instance, you could do a sort of perfect model experiments with your models, pretending one of them is reality, see what the effect of the double counting was on that, you know, and then use that to correct. You know, you can get an idea of how much it's affecting your confidence. You can play games with a bunch of models and pretend one of the model runs is reality, you know, and then see what the effect would be by, in a perfect model scenario, tuning things around and see if you could get some handle on that. You know, people haven't done much of that, you know, on the double counting.
Couldn't you go further and actually say that double counting was not ethical? It actually breaches scientific ethics to do that.
Yeah, the
problem. Strong statement to make.
Problem is your medieval ancestors didn't go out and measure observations. You know, if they'd been measuring observations in the Middle Ages, that would have been useful. But you know, we've only got a very short record of observations.
Oh, that's a different issue, isn't it? I mean, the thing is, if you're going to use.
If you had a nice long historical record, you could use part of it to tune your model, another part of it to assess your model. You could then be great. You know, but we haven't got that really.
I think double counting is a fact of life, isn't it?
I always ask this question in these Muckham meetings, partly because it was the only question I thought I could actually ask. I didn't understand what else was going on, but you know, the answer always came back. Oh, you can deal with this. You know, you can account for the fact that you're using data, and there seemed to be. Well, from the talks I saw, there seemed to be a lot of using, you know, taking a model in which there must have been some information, you know, the galaxy formation model, and using some of the you know, the data that would have been known about when that model was put together, in constraining it. So.
I'll ask Chris a bit more if you want for that. You know, I don't know if they came up with real big answers to it, but the feeling is it needs to be addressed. That, you know, that there's a danger that models can get over-converged together. You know, by tuning all the model, this idea of the evolutionary tree of models, there's a danger that we'll end up with one species, right? It might be the wrong one.
I mentioned yesterday the work of Knighting.
Yeah.
And if you have a consistent Bayesian framework and you do your calibration sequentially, starting as far back as you want to go, then as you calibrate, you can then use the observations before you use them to calibrate to test, so that you can sequentially test ahead of yourself. And in that way you avoid the double counting in the non-ethical way, but you use it in an ethical way, would be my. So you can double count as long as you test before you calibrate. Right. So you can use the data to test, then you can use it to calibrate, and you're okay. Would be my suggestion.
We need a fair trade climate model.
No, you can do a formal calculation of the distance you would expect between the model and the reality, given that you've used, as long as you use the reality in an explicit fashion to create your fit. At that point, everything is, you can do the simulation experiments, or you can even do exact calculations.
Okay, we should get a handle on
This is
that.
what we call the hat run calculation.
Yes, which is a bit like the hat matrix.
Exactly.
Yeah.
Well, it's a hat run. It's more
Yeah, yeah.
the sort of obscure basic. But you can do the calculation, provided you're explicit in how you use the data effectively to fit the model.
So maybe Michael can give you references on this. Yeah?
Well, I can give you references on what we do.
Yeah.
So we'll have a question at the front, and then I think we'll break for coffee.
Yeah, I've been listening to these talks this day already. In my opinion, my understanding is really that multimodal is not very important at this point. But it's, well, I always thought, I come from oceanography, that we decided to do some multimodal, much less than you do in climate, because it's a political decision. I mean, everybody wants to have their model in, so we put it everything.
It's democracy.
But so it's democracy. It's a consensus. It's more subjective Bayesian. I don't know. So it's fun. That's a matter of life, and it would be nice to have a nice tool, a statistical tool that has a consensus on which one is the model to use, and it's fine. But at the end of the day, I prefer to understand why my model is wrong. And so I found that this emulator framework, which is more on understanding what are the weak points of a single model and try to see what you can do with it so that you can understand maybe even the deterministic model, how to change it finally, because at the end of the day, I think we still have to ameliorate the deterministic model, a very important framework, which is a bit on, I mean, either you do the emulator or you do the multimodal, and in my impression is...
it's not either or. You can, no, you can do...
Because
ideally you do the emulation on a
finite
multimodal.
dimension of life, you know. You have so many things you can do.
The
So you have to decide which one.
The danger is one model, you could go down the road of, you've only got one view of the world that way, you know, so you could have a model that had no ENSO or something, or could have, that's why multi-model spans more than a single model can. I think I'm fair to assume about this. So when they did experiments of the meta-obvious on the comp, you can try perturbing your meta-obvious model a lot, but the amount of things it can do still doesn't look as wide as if you look at a multi-model. So multi-model is more diverse. You're losing diversity if you just look at one model.
You want to include all the information that you've got, I think.
Even if it is not physically meaningful.
That's probably one of the most useful bits of information. I think we're probably going to hear about multi-model approaches from Richard, are we?
Yeah. Are we? Yeah.
But I think we'll break now, and we're going to come back at 3:30 for an hour's discussion, John, which will be about...
well, I think David's actually going to kick us off.
Okay.
I think he might kick us off with that last slide, actually. I don't know what you were thinking, David.
If you want. I don't know. It's maybe do you want to say the idea... One of the feelings with the discussion session is that it will be... There are people at the Exeter workshop, but not everybody here was at the Exeter workshop. So this is your chance to sort of chip in and say ideas and things that you think are relevant to this and things that we might have missed. Or so it's, you know, over the tea break you can have a think about this and say, well, I didn't agree with that. Climate does exist, and you know, we can have a right old argument about this.
Well, findings and questions so far is, roughly speaking, what we thought might be the theme of this discussion. And you've got sort of like questions so far on both sides. So.
Yeah. Okay.